Hey guys. So it's been a while since I've made one of these videos, but I have been working a lot on C in the background. Now on my left side of my screen, I have my Antler grammar file. So if you've been following my sort of, I'd say disjointed series about making your own language, the most recent video, as at time of recording, is how to actually make a parser generator, or how to use a parser generator, in this case Antler, with Kotlin, so that we can just write a grammar file like this thing on the left and then have a parser made for us so we don't have to waste time actually just doing that by hand. Of course, as I've said in the past, it's nice to make a parser a handful of times so that you understand how they work, but you will eventually reach a point essentially where if your thing is like more complicated than like just some I was gonna say than something that isn't that complicated, but essentially once it becomes too complicated, you should just be using some parser generator library. So I just want to discuss some of the features I'm sort of thinking about for my language. So first things first, you can see the types on the bottom left of the screen that I'm planning so far. We have an any type, which represents, just like there's multiple ways that I could do it. It might represent literally anything, and then you have to cast it to make it work, sort of like a void pointer. But it also sort of just represents, it's like the type of null, if anything, like at least for now. Unit is just like, it doesn't return anything, but it does return control flow. So functions that would be void in C would be of type unit. I also realized I could probably increase the size of this. Let me do this like right now, which is the worst possible time to do it, but yeah. Okay, that's probably better. And then of course we have the familiar types, things like bool, char, and string. Now, I'm going to define bool as just a normal boolean. Character is going to be defined as a, so if this is like a C code, it would be something like type def char as just char. It's just going to be one-to-one, which means it's platform dependent. Like, if you're dealing in C code, the C language only guarantees that size of char returns 1. That's a guarantee. But that doesn't mean that a character will take up a single byte of memory. It just means that the size of operator must return 1, which is a really dumb thing, but the reason is you could have systems where characters are like, like 11 bits or 12 bits or 16 bits. And for portability, it's better to just sort of allow those things. Now, strings, I'm going to define strings as it's essentially a character array, but it's also going to be a bit more like Java, I think, and it's going to store its size, and it might not be null terminated, but I'm not sure yet. I'm not entirely sure. Now, next are like the integer types. I've sort of settled on this notation, so like in a language like Rust or I think Zig, you'll have like an I8, I16, and I do like that because it's like really compact and simple, but something I really like about Kotlin is that you don't have the like Java primitives of like int or boolean. You have the like container classes, and one of the consequences of that is all your type names are capital. And there's something nice about primitives being different, but I also just really like the idea that, okay, all type names begin with a capital letter. It just adds a layer of consistency, I think. So what I'm planning right now, but this could change. I could go back on this and do like an I8 to make it more familiar, but I plan on doing like a capital I8, I16, etc. And the way I'm going to define these is in C you have a, what is it, standard int, and in there you have a few declarations. So you have some exact size types. I think it's like int, like 16t, for example. I think that's how it's written. That would be the exact, basically at compile time, the compiler will create, or I suppose even, no, it would be at compile time. There would be some hash define this thing is equal to some type given whatever system you're compiling on. So often an int16 is just going to directly correspond to a short, I believe, but that's only if your short is exactly 16 bits. On other systems, it might correspond to something else. So the issue with C, right, is for portability's sake, they have these sort of types for integers, and their sizes aren't guaranteed. On most like on like x86 64-bit operating systems, an int is always going to be 32 bits. A long is always going to be 64, essentially. But that isn't true for all CPUs that you could possibly compile to. So the way that C handles that is, well, it just says that this one, it's something like this is less than this is less than this, and they can each store a certain amount, like a largest number at least. Like, that's essentially what it does. But in standard int, you have access to exact size types. But again, you run into the same problem of if you're compiling to some like embedded system, maybe they don't have a 64-bit type. Did I say 16.4? 64-bit type. And then that would break all of your code. So in order for portability, you actually have two other things for each size. There are like the int least 16T. I think that's how it's spelled, but I don't remember. It's not exact. You can look it up though. And then there's also the fast ones. So the least is guaranteed to be, it's guaranteed to exist for one thing. So like int 16T is not guaranteed to exist if your CPU doesn't support 16 bits. Because there are some architectures that are not like, you know, factors of like a power of 2. You could have like a 17-bit like integer or something. You could have like a 33, like 35, whatever. Like there's some weird architectures out there, and that wouldn't work on those. But the least 16 type is, I think it's guaranteed to be, it can hold, it's at least like 16 bits. It can at least hold like 2 to the 16 minus 1 or something in it. And you have to factor the fact that the first bit is for the sign, but that's essentially it, I think. But it's guaranteed to be the smallest type that works. So for example, if you have a 17-bit integer in your weird architecture, then int least 16 would correspond to like a 17-bit thing, but it would exist, you know? And fast, the fast one is like the least, but instead of optimizing for size, it optimizes for speed. So for example, on a 64-bit architecture, it's possible that dealing in 32-bit numbers is actually like really slow. It's possible that you could design a 64-bit architecture where 32-bit integers have to just be sort of mimicked. They have to be pretended in the way that in a 32-bit operating system, you'd pretend to have a 64-bit integer. So it's possible that 32-bit integer is actually slower than a 64-bit. So if you have int fast 32T, that could correspond to a 64-bit integer in your system if that is the fastest, because the fast types are essentially just saying it can hold this size, but it's guaranteed to be the fastest one. Whereas the least is saying it can hold this size, but it's guaranteed to be the smallest one. And so I have a choice, obviously. I'm not going to use the exact types because I want the portability of C for my language. Because that's really what my language is meant to be, is like C with handrails. You know what I mean? Like a bit more modern syntax, in my opinion. Obviously, everybody has a different opinion of syntaxes. But my opinion is it's going to be a bit safer and a bit more modern. So I could either use the least types, which would save on memory space, or I could use the fast types. And in my opinion, I think I'm going to compile to the fast types. I mean, worst case, I'll have a mechanism where people can just include standard int and alias this thing for themselves, and they can specify which they use. But my default integers, I believe, are going to be the fast ones. Because I think I just want to prioritize, you know, I think speed is more important, at least for desktop apps. It's more important than memory space. Plus, if you add like a size of operator or something, then people can choose at like compile time. If you could add like a mechanism for them to choose based on size if they need to. But I think I'll compile to the fast types just so that it ends up being as quick as possible, while still guaranteeing that it can hold at least that size. And the good thing about doing this is, like int fast 8T is guaranteed to be like less than or equal to, like int fast 16T is less than or equal to ... less than or equal to int fast 64T, right? So it's guaranteed by the compiler, by the C language, that whatever these things are defined as, they could all be the same thing, technically. They could all be the exact same type underneath, but they're guaranteed to have this ordering. And, in fact, it's also useful. This is something I haven't really included in the past, but it's also nice. You also have, like, an int I think it's int max t. And now that I'm thinking about it, I think the t is like that, but I'm not going to worry about it. You also have this guarantee, right? So because this is guaranteed in terms of size, I'm going to allow type coercion between, like, among the signed integers. And then I'll also allow them between the unsigned integers, but not, like, crossing over, if that makes sense. So you can't, like, implicitly cast an unsigned 16 to a signed 16, but you can implicitly cast a signed 16 up to a unsigned 32. Like, you have these rows where you can cast implicitly upwards because you're not losing information, but the rows are separate. And it will be the same thing with the floating types. So F32, in this case, is going to correspond directly to a float. And I believe by IEEE that's guaranteed to be 32 bits, hypothetically. I don't know if like the 32 actually makes sense, but essentially it's a 32-bit float on most systems. 64-bit will be the F64 for a double. And then F max in this case is just going to be a long double, which in principle is the largest like primitive one you can have on a system. So I think that naming convention sort of makes sense. And then there's one more type, which is size. Now, size is actually going to correspond directly to size t, because size t, you can't like neatly fit into like the unsigned integer sort of implicit cast row. Same thing with char, right? Because char could be signed or unsigned, and it could be 8 bits, it could be 16, it could be 32. So I don't know, so I can't allow implicit casting between those things. But size t, I believe, is guaranteed to be, it is an integer type that can hold the largest, it can hold like the value that represents the most amount of memory that a system can allocate, something like that. Where it's like if you have, essentially it's like if you created the largest possible struct object in C, and you did size of that object, the largest possible one, this type is just guaranteed to be large enough to hold that number, essentially. Like that's all it's saying. But that's of course different than the largest possible integer that you have. Often they'll be the same, but you can't assume that they'll be the same. So for things like this, I'm just going to have a size. And I think I'm going to call it size. And so you could do for loops or like certain loops, you could use this thing hypothetically. I'm still not sure if that's a really good practice. I've heard people say that it's bad because like it's in terms of memory, it's probably just bad because it's overkill because it's usually too large. But either way, it will be available for people to use. And so those will be the sort of like primitive types. I might add more, I might modify this, but I think for now that's about essentially what I have. Now arrays, I have two types of arrays kind of similar to Rust, where the notation is going to be something like this, I think. This is sort of where I've settled on. You could have you could do something like this, right? And essentially what this is saying is it's an array, which is the square brackets. The way you read this, right, because this is supposed to be readable, is it's an array of 4 elements, and then of course because the colon, it's of type I32, because this is how I designate types in my language, just like Kotlin, just like Rust. So essentially, you can read this as saying it's an array of 4 things of type I32. And to me, I think that's reasonable. I think Rust does this. It would do like I32, comma 5. I said comma, semicolon. I just don't like the idea of having a semicolon that doesn't end a statement. That seems really weird to me. And like the size also, it doesn't really matter which comes first, I don't think. So I think this is a good middle ground where it's like I'm utilizing an existing notation where it's saying like these are 5 things of type I32. And so arrays will need their size known at compile time. But then you could have something like a slice where you just specify the type. And it's like, okay, this is a slice of I32, and that size will be stored at runtime as like some, struct that has a pointer plus a size t or something. So that's my plan for arrays. And then data types are going to just be, essentially it's any of the primitive types plus arrays, plus you need identifiers so that you have like access to structs, and postfix expressions, because that's how I'm going to be doing namespaces. I'm not sure how I'm doing modules yet, but suppose I have like module. Suppose you have like a math dot trig dot py. Like this is how you would access it, because I just find in C++, using the colon thing, like, I like how the font ligature makes it look. It doesn't look bad, but it just doesn't look as good to me. And I believe the reason for that is because it's because of inheritance, I think, where you could have like a class that is inheriting from a different class. And if you do a dot, you can access the like superclass. But if you have a method of like the same name, you need to use like this or something. Like, it's really weird, but I'm not going to have inheritance in my language. I'm either going to only allow interfaces or I'm going to have traits, because I don't think that object orientation tends to be a good path the majority of the time. And I think the best things about object orientation, like polymorphism and stuff, you can access using just interfaces or traits. So I think I'll just plan on doing something like that. And that way it will be better than C, because in C you have to sort of just mimic having methods at all. And there's like no sort of generic system. But if I sort of make a type system kind of like Rust, then I think that will be reasonable. But I'll do namespaces something like this because I just find that more readable. And so that's why data types can take postfix expressions, because you might have something like this as a type name. So now we sort of talk about the more recent thing I've kind of decided on. I've gone back and forth about whether this language is going to be manual memory management or like a ownership model like Rust. I never really thought about making a garbage collector because to me it just feels like a waste of process, even though I am obviously writing this in Kotlin and I love the garbage collector for just dealing with it, but like, also I don't want to have to learn how to make one, if I'm being completely honest. So right now I'm planning on doing manual memory management, and my goal is to essentially make it safer, kind of like Zig. So the hard thing to me, right? One of the most annoying things in C that I discovered when I tried to like transpile stuff to C is, okay, you declare a variable here, right? And you have like an int pointer x, and this is equal to, in this case we can do it inline because initializer lists are kind of amazing, and we could just make an integer like this. And this will create, this is equivalent to saying like int temp equals 1, and then int pointer x is the memory address of temp. Like, this is just a way to do it inline, which is super convenient. So we can just declare a pointer like this. And that's all well and good. We know that x is a pointer to something on the stack. But what if we pass this thing into a function that expects some int pointer, right? Well, inside that function, it has no idea whether that pointer points to the stack, the heap, the data segment, something else, you know, like, it has no idea. So what I've sort of decided on, it's a bit complex, maybe more than it needs to be, but I do think references tend to be better than pointers because I just don't want to have to do any dereferencing or any of that nonsense. Like, that's kind of just a pain. So I'm going to create references in my language, but they're technically pointers, and they're kind of like pointers, but they're not like C++ references, because C++ you can't reassign them. But mine will be reassignable, sort of like Java references, if anything. But while they're reassignable, what am I actually getting at here? Basically, they're like pointers, but you access the data like a reference. That's basically the only way to say it. Now, I'm going to actually have 4 reference types. And this might seem like a lot, but so I'm going to have a hash to represent static references, $sign to represent stack references, % to represent dynamic or heap references, and then I'll have the normal reference symbol to mean any of the above. So the question is why? Well, because it would be nice to know where pointers are allocated. If you know that this pointer is a pointer to the stack, then whatever, like, I'm going to add some sort of either function or operator that will allow you to essentially call free, right? And if you pass in a pointer to a function and you call free on it, but it's a stack pointer, then that's, I believe, undefined behavior, and anything could happen. You could have some weird stuff happen. But if my language at compile time knows that this is a pointer to the stack, then it can tell you that you cannot free it. And so that makes the manual memory management safer. Same thing with the static. It might be nice to know that the lifetime of this thing is forever, right? It might be nice. Hypothetically, I could just merge these into like a dynamic and a non-dynamic pointer, but I think I may as well add the static one just so you have that option, right? So you know, like, this thing is a pointer to something that exists everywhere, and it might be a global variable, and it might be modified by something else. Like, it just gives you more information, essentially. I'll also not allow you to, if you make a variable inside of a function and return a reference to the variable that's inside the function, you know, a reference to some stack address right before the stack gets popped from the function, that's immediately going to make it invalid. I'm just not going to let you do that because that's really stupid. And I think what C does is it just says it's undefined behavior. But even if it might work, you shouldn't rely on that, right? So it's better that I just say don't do it. I think, like, I don't unless there's some like advanced memory technique where returning some pointer, again, if I have like my num is the address of some int of like value 5, and then I return this pointer, right? That pointer is immediately invalid. So, like, unless there's some weird situation where there's something valid about this, I don't think my compiler should allow this at all. In C, most compilers will just give you a warning, but I just don't think it should be allowed at all. There's no reason to, as far as I'm concerned. And suppose you pass in a pointer. Well, you can just detect that this one, like, this is an entirely different situation than this. Because this one, we know that this was declared here. Whereas this one we know was declared not here. So we know it will be valid because this is passed in from the caller and this is returned to the caller. So if this was valid in the first place, then this will still be valid. You know what I mean? Like, you can never get an invalid sort of state with this. Now, why have the, like, any reference? Because sometimes you don't care about where something is, you just care about the data, and you just essentially say this is someone else's responsibility. Also, if I allow you to use C libraries, there will be times when it will simply return like a pointer to something, or request a pointer to something, but it has no idea where that thing exists. So you would need some way of actually utilizing that, so you need some sort of like raw pointer, in this case a raw reference or whatever. What I might do, either this is just going to be like a raw thing, but I'm trying to think about situations where you could have a function that conditionally returns either a stack pointer in one condition or a dynamic pointer in another condition. And that could be valid code. Like, I don't see a reason to disallow that. So then, obviously, the return type would have to be of this type of reference. But then I need a way to detect that that thing was dynamic in the first place so that you could hypothetically free it after. So what I might do is I might make these pointers sort of like slices, where slices are safe because they know their sizes. Well, these pointers might sort of have an enum to represent like a state. This is like pseudocode, so like just bear with me. But basically, it could have some state where it's like, it could store this thing in like a single byte, where it's like static, stack, dynamic, unknown, right? Those could be like the 4 states, and it could just have one of these and a pointer. And then what you could do is you could do something like, suppose you have some reference and it's called X. You could say like X is dynamic as a condition, and if this returns true, then you could like call free on it or something, right? And that way at runtime you can determine where this thing is. But the only way to do that is to keep track of it, because I'll know at compile time where things that my program creates are. I won't know about the C language, but so if I use like a library from C in my code, I won't know where a pointer comes from, but in terms of mine, I will. And I could allow you to free unknown references as well, just in case, right? Just so that you know what you're doing, but you have to explicitly like cast it or something. So those are like my references. Now, Of course, immutability is kind of an important aspect too, isn't it, right? So I'm sort of leaning on a like symbol dense thing instead of like a keyword dense, because I find a language like Java is just too verbose and you end up with lines that are way too long because you're writing so much information. I don't really like the mutable keyword from Rust because it just looks like it's pronounced as mutt, and I don't like that because it really should be mute, but like you can't do that. It's like that. It doesn't feel like it's a good sort of shorthand. It feels like I just don't really like it. Plus it's kind of clunky sometimes when you have like like weird sort of stuff. So my solution is essentially references by default will be immutable, which is sort of like a functional idea. It's just sort of like by default you cannot modify this thing. In order to say you can modify it, you add an exclamation mark to sort of point out like this thing is dangerous. You can edit it and modify it. It's not read-only. And so you would just sort of combine these symbols, which is, a little clunky, but you could do like a shebang essentially where it's like this is a readable, or it's a mutable reference to an i32 that exists in the heap, well, in the data segment somewhere. It's some static integer 32, and through this reference you can modify it. Or if you had this, it's like, okay, this is a read-only reference. That's essentially my sort of way. I could add like an extra symbol for like, okay, this symbol means it's a static read-only, and that's like, nah, let's just do something simple. Add another symbol, which of course is going to be a little weird, but I think once you know the system, it's not going to be that bad. Lastly, there's one other sort of useful utility, which is it would be nice to not allow every reference to be null. So by default, if I have a reference to an i32 like this thing is read-only, and it cannot be null. If you want to make it null, you add a question mark at the end. So in the worst case, you would have something like this, which is a mutable reference to something that could be null. Which, like, I'm fine with that. Like, it's a little much, but I think it's reasonable. Instead of doing something like, like a const pointer to like a thing, and it's just like, once you start adding keywords into the types like that, it just becomes a huge mess. So, I haven't even talked about declarations of variables yet, but essentially, anytime you see the keyword var, you know that you are allocating memory. And that's something I also think is super useful, is like memory allocation should be very explicit and you should know when they occur. When you type the word var, that is going to allocate some memory. And you can place it in 3 places. You can modify it as static. You can leave nothing to mean auto, or you can explicitly say auto, but nothing will just be auto. And you can say dynamic. Now, I could just allow the like reference, everything could be a reference, and you could just have that through the type. But I think if you have a big chain of declarations, it's just going to be more readable to actually have the word next to it so that you can actually sort of see like, okay, that thing's static, that thing's not. And then you do like your name. So let's say we make some number here, and you never add the reference thing here, you just add everything else. But for example, you notice this is a num that's dynamic, which technically is a reference. Every variable itself is a reference, you just don't add this because it doesn't matter, so you're not going to bother. I might allow you to, hypothetically, but like you just don't need to. So we could then make an i32 that's dynamic, and this would just be a declaration, and what this would do is it would actually malloc the size of i32 in the back side, and it would make your reference equal to that thing. Now, you can then also initialize the value, which, here's the issue, right? What happens if malloc returns null? Well, if you have a dynamic variable, you can make this thing nullable, because at the end of the day, it is a reference. So what I'm going to essentially say, I guess, is this is like an attempted assignment, essentially. It could be null. If it isn't null, it will be assigned 5. But if it is null, because malloc returned null, then it will just stay null. And you can check. You can do like num is null to essentially check if it is null. Because the is keyword is going to check like equality, but in terms of the actual like pointer that it is internally built. But you see, this is so much simpler than if you did this in C, you'd have to do something like an int pointer. Pointer is equal to malloc size of int. And then you would have to say like if pointer, then the value of pointer equals 5. And essentially it's just going to be that, but it's all going to just be compacted so that you don't have to think about that. You can, in my language, you have to think about allocations and freeing, but you don't have to think about how you allocate essentially. You just say, this is a variable, so it's an allocation, and then you can just spit on dynamic and it will be allocated on the heap for you. What I think I'm also going to allow is you can say, I don't want this to be nullable. But there's two things that happen with that. One, if malloc returns null, then this thing needs to either make some sort of error or a panic or cancel the program or something. And two, it means you won't be able to free this thing. And there's a reason for that. The way I'm going to implement references, I need to... there's like two big problems with sort of manual memory. Obviously, there's a lot of like spatial temporal problems, but two of the big problems are null pointers. When you're trying to dereference null pointers, that's a problem. And another problem is when you free some pointer and then you try and dereference it or free it again, right? Like a double free or something. So what I'm going to do is I'm going to essentially say, when you do this, when you sort of declare this num, this is going to essentially be like this, right? Malloc, whatever. And in the assignment. If you make a reference to this, what you're actually going to do is make a pointer to a pointer. That way, if you free it through any of the references, if you have like 17 references in your program to the same variable, the same memory address, what I can do is I can take the reference and I can dereference it to get this pointer back and set it to null so that all the references will know that this thing has been freed and will be null now. Because that will then solve the like double free problem. Because if you free it again, well, you're just freeing null, so it's not actually a problem. And if you dereference it, well, there's safety mechanisms in place for when a pointer is null. You know, using like the safe operators and stuff that like Kotlin has. So there'll be mechanisms that will make it safer if it is null. And once you free it, however that happens, it will do that. But the problem is, this thing is not allowed to ever be null. Therefore, I can never allow you to free it. I'm still going to allow you to make things like this, but the issue is, because like hypothetically, right, you could, suppose, I haven't shown you how I'll make references, so I'll actually do that quickly. You use a ref keyword, because like I said, vars are allocations, and you say like ref, num ref is equal to, and you could specify type, or it could just be inferred, and it's just equal to num. Except actually there's a problem. How do you differentiate between reassignment of the reference and reassignment of the value it points to? So what I'm going to do is this. So you're essentially defining this reference to be a reference to that. And then if I want to set it from 5 to 6, I can do this. And then if I want to reassign it, I can do something like this, right? Essentially, I think that's what I'm going to rely on. But so this is how you're going to make references, but you can have two types of references. Auto references, like this one, but you might also want static references. And the thing is, in C, every global variable is static. It's just you don't have to explicitly say it. In my language, you will have to explicitly say it because you need to always know where things are allocated. And so the reason I'm allowing you to make static references is so you could have global variables that are references, essentially. Like that's the reason. Plus, it might just be useful to have a static reference to something. And so you can have a static reference to something that's a dynamic. That's fine. And you can reassign it and stuff. Yeah, so I was talking something about the dynamic not being freeable. Yes, so hypothetically, that could be a use case, right? If you have a static, suppose you have a global variable that's a static reference to this number, of course you'd have to do something like numref. You'd have to do something like this, and then in a function you could say, numref is defined to be this. Like, hypothetically, in fact, this isn't valid. I'd have to specify it is a... Specifically, it is a heap reference to 932 that is not nullable. Something like that, and if I want to be able to modify it, I'd do that, right? Pretty simple, I think. And then you could have your main function down here, and you could actually initialize this. So maybe it's useful to allow dynamics that can never be freed, because, you know, sometimes there's... Dynamic variables are useful for, like, multiple reasons, one of which is simply if you don't know the size at compile time. But sometimes you might need access to something for the length of the program, right? And the operating system will free it for you. So, like, the lifetime of this thing will essentially be static, I guess, in a sense. But of course, it isn't in the data segment. It's not part of the binary. It's actually just, like, on the heap. So, I think I'll allow this, but the majority of the time, you're going to want to make them nullable so that you'll be able to actually free it. I guess the other alternative is you could free it. Maybe I'll say you can free this, but only if you've never made a reference to it. That's probably the better thing to do, isn't it? So if you make this thing, you can free it down here so long as you have never passed it by reference to anywhere else. I think that's good. I don't see how that's sort of... I don't think that's a problem. I don't think I could detect, like, an ownership transfer, though, unless I add some sort of mechanism for that, where it's like, okay, I'm passing this dynamic thing to a function where it will exist, and it won't exist here. Like some sort of restrict pointer, right, where it can only be referred to by one thing. I could maybe add a keyword, right, where it's like, I don't know, like, just something, right, just some sort of keyword to represent that this thing can never be referenced. It might be nice to add something to, like, the var to be like, can never be referenced. That way there can be certain guarantees, and I could allow you to free this because it could never be referenced. Something like that. Anyway. So, that's a lot of the stuff, but I want to, like, demonstrate sort of how assignment is going to work. So suppose we make some variable, and this is just going to be an auto variable. It doesn't really matter where it is. But we can make some number, and we could just set this to, like, 16, right? And this is an i32 by default. We can then say, like, num is equal to, like, 5, and that will modify it. If you want something that is not modifiable, right, essentially equivalent to doing the, like, a reference, you can use... I was going to make it the val keyword, like in Kotlin, but Kotlin's val isn't really an immutable keyword. It's more of, like, you cannot reassign it keyword, right? Like, you can access members and not modify. But when I'm talking about immutability, I mean you cannot modify it or its members. Because I find that to be better, right? That tends to be a stronger thing. So instead of a val, which might be confusing, I'm going to have var and invar. So invar just is short for invariable, which is a word by itself. You have variables and you have invariables. And invariables are invariable. You can't modify them. So this would be an invalid reassignment. And this is also nice because then you still have the var, which means you only have to look for var to know that an assignment has occurred. So this reassignment would be invalid, this one would be good. But you can never modify it. Vars are references, but they're references to a single variable. They can never be, like, reassigned in terms of reference. They're always pointing to the same thing in memory. I'm just thinking about... No, that's all probably fine. But yeah, these are all pointing to the same thing in memory. When it comes to a reference, these things obviously, like I said, can be reassigned. So we could make a reference, call it num2, is a reference to num. Except this would be invalid because we need a way to differentiate, right? What if we want to say num2 is equal to 6, and that's actually going to change num to 6? But we don't want to change the reference, but hypothetically we could, and we can then come in here and actually change the reference to something else. Could also be null, actually, I suppose. Basically. Yeah, so I suppose after you free memory, it's all just going to be a reference to null. That's kind of just how it would work. There's another thing I want to say, which is, like I said, like I demonstrated actually, you can use like the C initializer list syntax to make like a pointer inline without declaring like the other sort of like, without making another variable. Well, I have something that's similar to that. And so suppose you want to make a variable inline. Well, there's going to be a operator called var, which takes in a type. And what you give here is actually the reference type. So you could say it's a variable that is a static, mutable f64, right? And it's static, so I'm not going to allow it to be null in this case. But this is going to be that, and then we give it an initial value, something like 16.6, right? And so you can then make inline references, but once again, you see the var keyword, so you know that in memory allocation is happening. In this case, it's going to be a static allocation. We could also just make it a heap allocation. That's a little bit of a weird ligature, but I guess that's fine. Or dynamic. And like that just allows you just like some more freedom when working in the language, because sometimes the way you deal in things in my language is going to be very different from a lot of others, because there's going to be times when you want to make a variable, but really what you want is a reference. Like any sort of uninitialized thing, right, is going to really just be like a reference most of the time. But I think this is good because I think it makes you have to think about, okay, what is actually supposed to be a unique piece of memory and what is actually supposed to just be a reference to something else, right? So for example, you can make a linked list in my language. It would be something like you make a struct node and you would make, suppose it has a piece of data, which should probably be an auto variable. Like I said before, auto is optional, but you can choose to specify. And this would be, hypothetically, I'll do some sort of generics at some point, and it could be like var value of type t. And then you could have a reference. In this case, it's probably going to be a reference of any type. I do have to think about this a bit because there might be problems, and I'll get to that in a moment, but you could have a... It should just be an auto reference. An auto reference of, you know, it's of node. And it's of type. It is going to be just some reference to a node of type T, right? Like essentially it would be like this. You don't need the autos. I don't allow you to make a dynamic reference, which essentially would just mean you could put the pointer in the heap. I don't really see the need, but you can technically mimic it a few ways. One way is if you have an array, you could have an array that contains a reference to something on the heap. Like this. Suppose I32. And this would be an array, a size 1, that contains a reference to this thing, and then you could make a reference to this, and you'd essentially have a reference on the heap. Another thing, though, is structs, right? These things are auto. There's a reason I say auto and not stack, mostly because that's what C does, but I think C does it for the same reason, which is, well, suppose we make a variable, and let's make it dynamic. Let's make a dynamic var linked list, which is going to be, I don't know how I'm going to do constructors yet, but suppose it's something like this, and I'm going to just initialize this thing with the value of like 2 or something, right? Like just something like this. Well, this node has to now be dynamic. So these auto variables, auto meaning the compiler chooses, it's not actually going to be on the stack. They're all going to be dynamically allocated. And so this reference is going to be dynamically allocated. And so is this node T reference, which is another reason why I need these references to anything to know where the thing is. Because if I want to like free the whole linked list, I'm going to need to know that these things are actually dynamically allocated. And the way I would sort of figure that out is because I know that this linked list itself is dynamically allocated and these are auto. So by being virtue of auto, since this is dynamic, they are dynamic, essentially. You would just trickle your way up, right, to figure out where they are. But it would be something like that. It would work, right? Like you could do this and you could have like a doubly linked list pretty simply. You don't have to worry about like the ownership stuff where it's like you have to sort of twist the language's arm to sort of make it work, as far as I understand, where it's like, how can you, like, getting references to multiple things, it just seemed like, to be honest, I have not really used Rust and I don't know much about the ownership system, which is really why I'm not designing it, because I don't understand it well enough to make it myself. But I think a system like this that allows manual control over memory, I think I understand it well enough to design it, and I think it's going to be overall better. Although in this case you really would want this to be nullable, wouldn't you? Because that's the whole way a linked list works. But it would just look like this, right? Like if you don't know how the syntax works, it might be confusing at first, but once you learn it, it's like there's just a handful of rules to declare about references. But like that's it, right? It's like really simple. It might be misleading in the sense that a reference appears to not be an allocation, but it is an allocation of a pointer. It's just, it's like in principle a struct, a var. If you're making a var to like some massive struct, that's going to be a huge allocation, whereas a reference to it is just going to be like 8 bytes or something, which is still very large relative to primitives, but at least it's pretty clear, right? Like var, you know that this is going to be initialized. Ref, it may or may not be. It all depends on whatever you're doing. But so this is sort of where I'm working on and where I'm at with C right now. And so I'm still sort of figuring out all these like edge cases and what I want to be there. But other than that, that's essentially, it's really like that double reference thing that is really going to help with safety, I think. And I think it's going to work the way I expect, where once you have something that's dynamic or whatever, something that can be freed, because only something dynamic can be freed, it will simply always be like a pointer, right? It will always be something like this. And then a reference to it can just be something like this, which is equal to the memory address of X. And then if you want to free X through the reference, you essentially say, we would free the memory address of X, which is stored as the dereference of the ref, which is a little confusing. And then you set the deref of the ref, which is X. We're setting the pointer X equal to null by reference, right? And then if you have many different references to this same thing, then all of them will instantly become null and can instantly be checked at runtime whether they are null. And that will allow for safety mechanisms, because you can access properties of these references by doing something like this, where it's a safe access, right? It will return null, I guess. I'm not sure, because there's a bit of a difference between nullable and optional. I kind of want to introduce like an optional thing, but that just seems like more of a hassle. I think you could get away with just using references that are nullable to represent that in this language, and it would be safe enough because of these access things that it's probably fine. It's really a lot like Kotlin and Java, but without the garbage collector and without the bad type generics, right? Because that's really the problem with Java, is like, they did some weird thing when they added generics for backwards compatibility, where they like erased the type at runtime. So you can't actually do like real runtime generics and stuff, and it's just really weird. Plus, of course, the garbage collector and the whole virtual machine's like a lot of overhead, hypothetically. Whereas this, it's similar syntax, but it's at the end of the day, it's compiling straight to C code that you could write yourself. It's just the language is forcing you to go through this path. So you either have to access things through safe operators, or you have to assert that this thing is not null. And if it is null, either it's going to be undefined behavior, but you explicitly say you're opting into that with this operator, or I'll have some sort of handle for that, where it either panics immediately, which would be helpful, because sometimes it is more helpful to have it crash a lot, and so you can actually figure out why, instead of having it just work sometimes, and then when you put it in production, it crashes. So I could either do that, or I could just, I could leave it as undefined, but like, I'll figure that out when I actually get there. The only other thing I want to say is, I might want to add 2 different types of print statements. It would be kind of nice to just have like a debug print statement that just exists in the language, but it only runs when you have like the debug option in your compiler. You know what I mean? Like, because there's so many times when you're just programming and you want like a print statement, but sometimes you don't remove the print statement and then it prints during like the finished program. So it'd be nice if you just had like a debug print statement immediately available. And then when you choose to compile, you'd have to be like dash dash debug or something, and then that's just how you'd build it, and those statements would run. But then when you actually compile it, they would not even exist in the finished product or something. You know what I mean? Like, that would just be kind of convenient. But anyway, I think that's going to be all there is for this episode. It's a lot of rambling, but I've really just been thinking about this the last few days. Also, I'm not sure about this const syntax, but essentially all it's doing is it's essentially just a hash define. It's just saying make a compile time constant. I might change the keyword. I might change it to like define. If I'm being honest, I'll probably end up doing that, because const is sort of like, it feels like it refers to other things that we're sort of familiar with. And you might get confused and think it's a variable, but it doesn't have a memory address, right? It's just a hash define. It's a preprocessor thing. So I'll figure a thing out for that. But yeah, I hope this is sort of interesting. If you've actually made it this far, then that's very impressive, and you enjoy rambling about complex topics. Good for you. But hopefully I can actually make progress on this language now. The hard part's going to be designing the type system, because like I haven't studied type theory. I sort of have a basic understanding of how it works just through experience, and I can kind of make a type system, but I have to sort of figure that out. Plus I have to make functions and function pointers, which is going to be its own thing. But yeah, also I should just add, while I'm here, I finally understand something that I didn't really understand for a long time, and it's one of those things that people in C++ will probably tell you, but it's sort of like, it makes a lot more sense now that I've seen it. Basically, when you use a string literal in C, and this is like a hello world, and we initialize some character to this, and we say, or some string like equals hello world, right? Actually, as far as I understand, I don't know if it's guaranteed, but at least often the compiler will simply, I think it might be guaranteed, the compiler will often write this string directly into the object file. If you look at the assembly of your C file, you'll see the string in there. And so actually, this string, it looks, if you're looking at a language like Java, right, you're actually allocating a new string and then you're copying it over. But with this is actually a pointer to the static object that is this thing. And realistically, right, this is, if I put this in my language where you can actually see the type, this would be a reference called string, which would be of type. It's a static immutable reference to a str. I might make it string, but str is probably fine for now. It's a static immutable reference to a string. So I think what I'm going to do in my language is, you could do this, right? You could make this reference because that's useful so that you're not wasting memory. But if you said like var s is equal to hello world, every time that you use the equals operator, oh, actually, yeah, every time you use the equals operator, you're going to be copying. The equals operator will always copy. So you'll be allocating a new string and you'll be copying this value over to it using this. When you use this, though, you're just going to be making a reference to it. I think that's actually a good way of doing things. So that way, you know when copying is happening. Copying is always happening anytime that you use the equals. For small things like an integer, that's not really a problem. But for a string, you really, unless you want to modify this thing, you probably really don't want to actually initialize it this way. You probably really would rather say it's a ref string, and it will infer this type just because that's what the type of this expression is, right? It is a immutable static reference to a string. But that explains some of the weird behavior in C, where, like I've said before, if you have a function that returns some pointer, that pointer is to some stack memory, right? And so it goes invalid immediately. But because these string literals exist in the data segment of memory. That's why you can return a string literal from this function and it works, because this actually doesn't exist on the stack. Even if I say char string and I make like a pointer, this really should be a const pointer because you really should not modify string literals, that is undefined behavior. But if I then return this pointer, this works. Even though the pointer itself will be deallocated, but the memory address it's pointing to is actually a static memory address, so it works. And so I finally understand that. But that's one of those things, right? I didn't know that global variables in C were static. I didn't know that string literals were static, because how are you supposed to just know that without actually looking at the assembly that it makes? In my language, you will know that, and you will have to know that. And I think that will benefit you to actually know where things are in memory when you're doing manual memory management, instead of just making assumptions that end up shooting yourself in the foot, right? Like, if you didn't know where this is, you wouldn't know that this code would even be valid. And you would just think, oh, I guess this is always valid, or like, oh, this is weird, but I guess it works. Like, it works for a reason, but C doesn't tell you the reason, but I am going to, basically. So I really should stop rambling at this point, but that's most of the interesting stuff I've done in the last few days when it comes to this. Once I figure out how to make a type system, I'll actually make a video about it, but that might take some time. So anyway, I hope you guys enjoyed. I'll see you in the next video.